says the following, that if we have f, this, complex numbers, holomorphic, and we have that the ball of radius r of z0 is contained within omega, actually, its closure is contained within omega, then we have that f of z equals 1 over 2 pi I, the integral around the boundary of the ball of f of zeta minus z d zeta for any z inside the ball. Okay, give me a sec. For any z inside the ball of radius r around z. Okay, so this is the statement that we have, right? Yeah? And we learned what this meant in the context or in the situation of putting the z exactly on the z0. So here's the picture. We have some ball like this, some radius like this, right? And we took some z inside this, yeah? And we can find out what this value is just by integrating around the boundary of the ball this weird-looking expression, yeah? And in a particular situation, when you took z equals z0, then this thing just reduced down to taking the average around the boundary of the ball of the real value part plus I times the average around the boundary of the ball of the imaginary part, yeah? That's what we found out, yeah? So the meaning of this is very natural or very understandable in the case when we stick in z equals z0 into this formula. Yeah? And later I will show you actually that this formula can be deduced from the mean value theorem. So it looks a little bit kind of just complicated and unnatural when you first see it. But it is just, at its heart, the mean value property for the real and imaginary parts. And that follows because they are harmonic functions, and we'll talk about that later going forward. So this is one of the key formulas we're going to have in this course. This is one of the key identities. It's going to give us an incredible amount of stuff. And the first thing we're going to do, of course, is just to prove it. So how are we going to prove this? Well, we're going to use the stuff that we've learned already. So we have some point like this, z, yeah? And we are going to create a keyhole contour. Actually, maybe I need to create a bigger picture. Let me do a bigger picture like this. Okay. This is z0. We have some z like this. And we're going to create a keyhole contour like this. We're going to put a little circle around here of some small radius, and then we're going to go up like this and up like this. Okay, and we're going to let this thing be delta. Okay, and then we're going to go around like this, like this, like this, like this, like this, like this. So this is our keyhole contour. Let's write this way around. All right, so notice that we're going anti-clockwise around the bigger circle, and then we end up going clockwise around the smaller one. Yeah? Cool. All right, so first claim is that this keyhole contour be denoted by gamma of delta alpha, where alpha is the width of the small little circle here. Okay, This is our keyhole contour. And our first claim is that when we take this function like this, and we integrate over the keyhole contour delta alpha, f of zeta over zeta minus z, dz, yeah, we claim that this is equal to 0. Tell me why this is true. Why is this true? So we're thinking of this as a function of zeta. Z is just fixed, right? It's this ball here. So is our theorem inapplicable because we consider this function, f of zeta over zeta minus z? Does that mess things up for us? How would it fail? How would it mess it up for us? It would mess it up for us if this function here failed to be holomorphic, yeah, on the closure of the interior of this keyhole. Yeah? Is that the case? Does this thing fail to be holomorphic on the closure of the interior of this keyhole? No, because the only problem we have, the only issue, was when zeta is equal to z, right? Then we have a singularity. But this keyhole avoids that, right? So on the interior of this keyhole and on the boundary of this keyhole, it's analytic, right? Yeah. In fact, we can just apply this theorem. So this closure of the interior of this keyhole is inside a domain on which this function is analytic. Yeah? On which this function is analytic. Yeah? Cool. So by the previous theorem, this is true. Is analytic on interior of the keyhole closure. Cool. So that is kind of a nice thing, because what does that mean? Well, if we look at this somewhat carefully, what we see is that it doesn't matter how small delta is, right? This remains true no matter how small delta is. Yeah? So it's also true. So we take the limit as delta tends to 0 of this expression this thing is equal to 0, because it's equal to 0 for every single delta. Yeah? Cool. All right, now look at this expression here, the limit of this integral. What will the limit of this integral be? What happens as we let delta tend down to 0? What do we get out from that expression? Indeed, why? Why so? Yeah, because alpha's fixed and we're letting delta get smaller and smaller and smaller, right? So what we're doing is we have this function, which away from z is a perfectly nice differentiable holomorphic function, right? And we're integrating from here to here, and then later we're integrating from here to here. Yeah? And if these things were exactly on top of each other, we would know that they would cancel out. Yeah? But they're not quite. They're not quite on top of each other. There's this tiny delta. But being a differentiable function, it's also continuous, right? It's also continuous. So the difference between the integral from here to here, as opposed to the integral from here to here, yeah, if we, i.e. in the same direction, so the integral from starting here to here compared to the integral starting here to here, yeah, the difference between those integrals is incredibly small, right? It gets smaller as delta goes down to 0 because, again, f is, or this expression here is continuous. Do you see what I mean? Yeah? So in the limit, this entire thing will just reduce down to the integral of these two circles. Now, I can add more details if this isn't clear to you. Do this if you want more details. Okay, let's do some more details. So without loss of generality, we can assume that this line segment is on just the real line, and the one next to it, which is parallel, is just up a little bit. Yeah. So consider this. Consider a holomorphic function h, where we take the integral from, say, 0 to some a of h of z dz minus the integral from I times delta, and then a plus I times delta, and we're going from this to this, this to this, in this direction of h of z dz. Consider that. Yeah? We can just give ourselves a parameterization. So the parameterization we'll just do here will be just z of t is just equal to t, because we're going along the real line. That's the easiest choice. Yeah? And the parameterization here we'll do is z of, or let's call this one z1, let's call this one z2. So z2 of t will just be I times delta plus t. Yeah? Because we have this line, and then we have a line which is just a little bit above it. Yeah? So then these guys turn out to be the integral from 0 to a, yeah, just h of t dt, yeah. This goes off. First parameterization, let me put it up here. So we're taking the parameterization z1 of t is t, that does the first job. z2 of t is equal to I times delta plus t, yeah. And the derivative of both. So we're using these two parameterizations right here, and the derivative of both of them is just equal to 1. Yeah? Yeah? So then this thing here turns into this thing, and this thing here turns into the integral from 0 to a of just h of t plus I times delta dt. Yeah? Cool. So then what is this? If we take the absolute value of this, it's less than equal to just the length that we're integrating over, and then the supremum over the difference between h of t minus h of t plus I times delta. And I know that's hard to read off the edge there, where t belongs to 0 to a. Yeah? And everything is continuous, right, inside an open set that contains both of these intervals. Yeah? So we can just let t go down to 0. Yeah? So again, we just let delta go down to 0, and then this quantity has to go down to 0. Yeah, because if it wasn't true, then we'd just pick a subsequence for which was false, extract a subsequence which converges, and would contradict continuity. Are you everyone with me now? Okay. So we do indeed have that as we let this delta go down to 0, these lines will ultimately just cancel each other out. Yeah? So all we'll end up with is this integral like this, going clockwise around the little circle, and the integral around the big circle. That's all we end up with. Yeah? And going clockwise around the little circle is the opposite orientation, so it's a minus. It's minus the normal integral going anti-clockwise. Yeah? So this thing is equal to 0, but it's also equal to the integral integral of the boundary of the bigger circle, which is radius r, around z0, right? This expression, f of z, or f of zeta, minus zeta minus z, v zeta, yeah? And then minus the integral of the little circle. And the little circle is radius alpha, but now it's around z, not z0. Yeah? So in other words, what we have is that the integral of this thing is equal to the integral of this thing. I should say that better. This integral is equal to this integral. as a consequence, yeah? So we start off with an integral around the bigger circle, and we end up with an integral around the tiny, tiny circle around our point z, yeah? Cool. So I'm going to raise the board, and we're going to see how that helps us. So try to remember that we've reduced this integral here to the integral around a little circle around z itself. Z we've chosen as just some point inside the ball. We were to the point of understanding that the integral 1 over 2 pi I, the integral around the bigger ball, BR of z0 of f of zeta minus z dz is the same as 1 over 2 pi I, the integral around this little ball, be alpha, now around z, not z0, of this thing, f of zeta minus z dz. Okay? Now, let's make a trivial adaptation to this. Let's write this as f of zeta minus f of z plus f of z, which for sure we can do. We can add and subtract something without changing anything, yeah? D zeta. Yeah, that's clearly true. Yeah? And then let's break up that thing. So that thing is 1 over 2 pi I, integral around the bound with the ball of radius alpha of z. And then this thing, f of z minus f of zeta minus f of z, zeta minus z d zeta, and then plus this thing, right? The 1 over 2 pi I integral around the boundary of the ball of radius alpha around z, now f of z over zeta minus z d zeta, yeah? Okay, cool. Now notice, f of z is the number we chose at the beginning, right? Inside the ball. We're doing all the action, all the integrations in terms of zeta, yeah? So this thing we can just pull outside the integral. We could just pull it directly outside, yeah? Let's do that. So it is not part of the action of the integration. It's just a constant for our purposes. Let's just pull it directly out. So this is 1, and then this thing here is just f of z. Yeah? Cool. Now, let's try and understand this expression here in the blue box. So in the blue box, what do we have? We have f of z over 2 pi I, and then just the integral of this function over the ball. But this is a function that we can easily just actually calculate, putting in a parameterization. So the obvious parameterization around the ball is the one which you would, you've told me before. Let's just take z of t to be equal to z plus alpha e to the it. That's a nice parameterization of the ball of radius alpha around z, yeah? And what is z prime? That is equal to I times alpha e to the it. Yeah? Cool. So let's directly calculate what this thing in the blue box is. So integrating from 0 to pi. Like this. And then we put in the stuff. So we're going to have 1 over, now, zeta, we're going to write it, it's going to replace by z of t, and it's equal to this thing, so the z's cancel. So over here, we're going to have alpha e to the it. Yeah? And then we're going to have z prime, which is equal to I alpha e to the it, like this. And we're integrating with respect to t. Yeah? So this thing turns into this thing when we use this parameterization z of t. With me? Yeah? Cool. And then we notice that this alpha e to the it and this alpha e to the it just cancel. Yeah? Yeah, they just cancel. So this is just equal to the integral of 1 from 0 to 2 pi, not pi, to 2 pi, going all the way around the circle. Yeah? So this is just the integral of 1 from 0 to 2 pi, it's just equal to 2 pi. Yeah? So this thing here just ends up being 2 pi. Yeah? And that's going to cancel with this 2 pi over here. Oh, not quite 2 pi, it's 2 pi I, because this I remains. Yeah? So this 2 pi I is going to cancel with this 2 pi I underneath here, and then this thing just does indeed just give us f of z. Yeah? So the stuff in the blue box is actually the stuff that we want, right? Stuff that we want. Yeah? But we have this other term. We have this other term over here. So let's look at this. Look at this guy here. Yeah, what are we doing? We are integrating this function, yeah, around this small ball. Around this small ball. Yeah? Cool. All right, so what would happen if we parameterize this? So let's put a line here, and let's do the red box over here. What would happen when we parameterize it is we get 1 over 2 pi I, and then the integral around 0 to 2 pi, and then we're just going to have this expression here. So we're going to have f of z plus alpha e to the it minus f of z, and then on the bottom we are just going to have just alpha e to the it, and then this is multiplied by, let's put it over here, z prime of t, and z prime of t is this thing here, so it's just I alpha e to the it dt. Yeah? Cool. All right, so tell me about this. Let's change color. Where's my blue? Tell me about this thing here. As alpha gets very, very small, what is this thing here tending towards? Just the derivative, right? Because it's a differentiable function. Yeah? So if we insist that alpha is small enough, then this thing minus f prime of z is less than any epsilon we want. Yeah? Yeah? And in particular, this thing will be a bounded expression. It'll be a bounded function over the circle of radius alpha around z for some small enough alpha. Yeah? Because it's within epsilon of this particular fixed complex number, f prime of z. Yeah? Yeah? So we can, for example, find alpha small enough so that the absolute value of this thing is less than twice f prime of z absolute value. Yeah? Because it's less than, it's because it's as close as you like to f prime of z plus some error of order epsilon, right? Yeah? So we can guarantee it's less, the absolute value of this thing is less than twice the absolute value of f prime of z. Are you with me, everybody? Give me a thumbs up if you're with me. All right, cool. So this thing, for small enough alpha, is just a bounded thing. It's bounded explicitly by something we know, twice the absolute value of f prime of z. Yeah? What about this thing? Well, this thing is just a complex number whose absolute value is equal to alpha, right? Yeah? Yeah? So we're integrating something from 0 to 2 pi, multiplied by a bounded thing, times something which is absolute value bounded by alpha. So if we take absolute values through inside this thing, so if we take this thing is less than the absolute value of everything inside here, yeah, then that is going to be less than just 2 f prime of z. I should write 2. Well, we're going to have the 2 pi will cancel with the 2 pi. So this is going to be less than or equal to this thing times just alpha, like this. Yeah? So as alpha tends to 0, this entire expression tends to 0. Yeah? Which tends to 0 as alpha tends to 0. So the red box, this thing, will just tend down to 0 as alpha goes down to 0. Yeah? And since we have that this formula is true for any choice of small alpha, this means that this thing, yeah, is actually just equal to this thing, yeah, which we showed was just equal to f itself. Yeah? Cool. Yeah? Because alpha can be made as small as we like. So this thing is not going to play a role. Yeah? Formally speaking, for any epsilon bigger than 0, we can show the difference between this and this is less than epsilon. And it's true for every epsilon less than 0, so these things are actually equal. Everybody with me? Give me a thumbs up. Okay, cool. And that's it. That's the proof of the mean value theorem, right? We've shown that this is equal to this.